15 billion years ago, a tiny nucleus smaller than a speck of dust expanded in a big bang and formed our entire universe. For decades, scientists have tried to understand this singular event. How did the Big Bang happen, and why? The origin of the universe is one of the oldest scientific questions, and perhaps the actual origin of science. Today, the scientific community still has no final answer, but many pertinent questions. Some of them can only be answered with telescopes in space that look from high above the Earth's atmosphere deep into space, into the most distant regions of the universe, at events that happened billions of years ago. Since the early 1970s, the European Space Agency has launched scientific space missions. Many unexpected results have changed the way we see the universe today. The Hubble Space Telescope, a joint ESA and NASA project, has made some of the most dramatic observations in the history of astronomy. Operating high above the disturbing atmosphere, Hubble has looked back far into the history of the universe. Hubble has detected huge black holes, colliding galaxies, dying and newborn stars. And it has ascertained that the expansion speed of the universe is different from existing theories. With a strong European contribution, the Next Generation Space Telescope will be ready in 2009 to see even farther and see the very first galaxies shortly after the first light ignited. But most objects in space hide themselves behind clouds of cosmic dust. That's why astronomers watch the universe not only in visible light, but in all wavelengths, ranging from energetic gamma rays up to long wavelength radio waves. ESA's Integral mission will capture the violent gamma ray sources deriving from neutron stars and accretion disks around giant black holes. It will also scrutinize the current theories explaining how heavier chemical elements are produced in the nuclei of stars. Integral will be launched in 2002. Distant galaxies and giant black holes often also emit X-rays. These are detected by ESA's XMM Newton telescope, the most sensitive X-ray observatory in space, launched in 1999. The spectacular findings of XMM have proven for the first time that black holes can release energy into space, which is contradictory to former theories and the general principle that nothing can escape the grip of a black hole, not even light. On the other side of the energy spectrum, telescopes can determine hidden celestial bodies by detecting the infrared light they emit. ESA's ISO satellite, launched in 1995, has found some of the most active star-forming regions in very remote galaxies. The Eddington orbiter will follow up on these discoveries, searching Earth-like, perhaps even habitable planets in distant solar systems. The Future Infrared Telescope of the European Space Agency is named Herschel. After its launch in 2007, scientists expect a new insight into the principles of galaxy making and the forming of extrasolar planets and protostars. Beyond the infrared, a new microwave detector will look even further back into time. The Planck orbiter will see the first light of the universe that is still filling space as a frozen background radiation. And it will hunt for traces of the first elements that once filled the entire universe. If Planck discovers anomalies in the cosmic background radiation, this will change our understanding of the way in which the Big Bang took place. Today, this is the farthest point to which technology can go, but theories go far beyond. Before the first light occurred, matter and antimatter filled the expanding universe like dense fog. This fog was opaque except for gravity, the force that holds matter together as stars and planets. As the universe cooled down, the first atoms of hydrogen and helium formed. 300,000 years after the Big Bang, the fog of hot matter became cold enough to clear, and the first light passed through. ESA is already preparing for a mission called LISA that in 2010 could look behind the fog of hot matter and detect the legendary gravitational waves that traverse the entire universe. Probing Einstein's theory of gravitation in space might shed new light on how this force can be unified with the other three fundamental forces, which are the strong, the weak, and the electromagnetic interactions. This unification is one of the main objectives of modern science.